Turn our attention to what was at one time an extremely important rule, Descartes' rule of signs. It was an avenue to find and limit the number of possible rational roots, for example, irrational zeros. You remember the P over Q rational zero theorem? Well, depending on what your lead coefficient and what your constant term are, you might have dozens of possible rational zeros. Well, with Descartes' rule of signs, this was a way of trying to limit what they might be. And so we're going to run through this now and do a couple of examples to kind of show you. Let f be a polynomial with real coefficients and a non-zero constant term. Okay, if the constant term is 0, which means there's no constant term, you would go ahead and factor out the smallest power of x that's common to all the terms, so that your constant term would become just that, a constant, something other than 0. So if the if f is a polynomial with real coefficients and a non-zero constant term, then 1, the number of positive real zeros, positive, is either the same as the number of sign changes in f of x, or is less than the number of sign changes in f of x by a positive even number. I'll explain that in more detail with an example. But it's either the number of sign changes, or it's the number of sign changes minus 2, minus 4, minus 6, subtracting a positive even number. The number of negative real zeros is either the same as the number of sign changes in f of the opposite of x, or, just like in the other, less than the number of sign changes in f of the opposite of x by a positive even number. This gives us an idea of how many positive and negative zeros, real zeros, there are of some polynomial. Now, of course, that doesn't help us with imaginary, because imaginary numbers that are truly imaginary numbers are neither positive or negative, but it would help us with the real zeros. So let's look at this example here. Determine the number of positive and negative real zeros. Well, if you look at this, first off, you want it in descending order, and this one is. If you look at f of x, notice how it goes from positive to positive, from positive to positive, from positive to positive. There are no sign changes. That means there are no positive real zeros. Now we look at f of the opposite of x, which would be 4 times the opposite of x to the 5th, plus 6 times the opposite of x to the 3rd, plus 2 times the opposite of x squared, plus 6. And simplify this, I'm going to have 5 factors of negative, so this is negative 4x to the 5th, minus 6x to the 3rd. Signs are changing now. It won't change here because the negative times the negative is positive. So plus 2x plus 6. Now if this is going from negative to negative, from negative to positive, there's a sign change. And from positive to positive, no sign change there. So I only have one sign change. I have one sign change. Therefore, I have one negative real zero. Okay? Now it's degree 5, so you think, well, you could have as many as 5 zeros. You only have one negative real zero, no positive. Well, that would mean that the other 4 zeros are imaginary numbers. Now let's look at the example over here to my right. Determine the number of possible positive and negative real zeros. And notice here, I gave you a little bit longer polynomial, and it's not in descending order. That's the highest degree. So I'm going to rewrite this as negative 5x to the 7th, plus 8x to the 6th, plus 3x to the 5th, minus x squared, minus 3x plus 1. And I'm going to look for sign changes to see how many possible positive real zeros there are. Well, this goes from negative to positive, so there's a sign change. Positive to positive, no. Positive to negative, yes. Negative to negative, no. Negative to positive, yes. I have 3. So the number of possible positive real zeros, zeros, there we go. Well, I could have as many as 3 because it's equal to the number of sign changes or less than the number of sign changes by a positive even number. So if I subtract 2 from this, I could have 1. Now if I subtract 2 again, I could have negative 1. Well, that doesn't make sense. You can't. This is the number of possible real zeros, not their actual zeros. So it either has to be 3 or it has to be 1. Now to check for negative, I'm going to come back to here. I'm going to find g of, it was g, right? The opposite of x be negative 5 times the opposite of x to the 7th plus 6 times the opposite of x to the 6th plus 3 times the opposite of x to the 5th minus the opposite of x to the 2nd minus 3 times the opposite of x plus 1. Just snuck it in. So simplifying this, since this is to the 7th power, this is going to be negative times negative is positive 5x to the 7th. This is going to be positive because it's to an even power. So that's going to be plus 8x to the 6th. This is going to be negative because it's an odd power. So this is going to be minus 3x to the 5th. This is positive with a subtraction there. So this is going to be minus x squared plus 3x plus 1. Well, I don't have a sign change here from positive to positive, but from positive to negative, yes I do. From negative to negative, no. From negative to positive, yes I do. From positive to positive, no. So how many are the number of possible negative real zeros? Okay, well, I have 2. Or I can subtract 2 from this because, again, or less than by the number of sign changes by a positive even number. So if I subtract 2, I might have 0. Now you say, well, wait a minute now. This thing's got 7 zeros. You're only accounting for maybe at most 5. Well, the other 2 would be imaginary. And it's possible, look, you could have 3 positives, 2 negatives, all reals, and 2 imaginary. Or you could have 3 positive, no negative reals, and that would give you 7 imaginary. You could have 1 positive and 2 negative real zeros, and that would leave 4 imaginary. Or you could have 1 positive, no negative, and that would give you 6 imaginaries. And it's always an even number because with imaginaries, remember the conjugate theorem, if a plus bi is a 0, a minus bi, as long as you have real coefficients. So that's what's going on here. And you can see that that would be useful because there's a lot of possible combinations for some of these rational roots. Now this one's not too bad because that's prime and that's prime. But if you had one that maybe this was negative 50 and this was 100 or something like that, or 144, you'd have all sorts of possibilities. Whereas if you can find 3 positives right off the bat, you don't have to look any further. So, fairly useful theorem at one time, not quite as useful anymore because technology. Almost always because of technology. Now this one is a little bit different than the Descartes rule of signs. It's more like from what we were looking at in the last video, but as you can see, it's circled in red there. So this is an example that you would find on the semester exam review. Use synthetic division and the factor theorem. Find the remaining zeros of the polynomial function if 1 0 is given. Now we've done problems like this, but these are right off the review. So I'm going to run through this first. I'm going to use synthetic division. By the way, if 4i, which is like 0 plus 4i, real coefficients, that means 0 minus 4i would be 1 as well. So we'd actually have 2 possible roots there. So I'm going to go with, where am I at here? I'm going to go with 1, negative 5, 16, negative 80, and I'm going to use 4i. So that's 1, that's 4i, that's negative 5 plus 4i. Multiply here, that would be 16i squared negative 16 minus 20i Well, if you add down this way, the 16s cancel, so that just gives me negative 20i, and if I multiply here, that's negative 80i squared, which is positive 80, 0. Well, we knew that was going to be 0 because it was given that it was a 0 of the function. So now I'm going to take the depressed polynomial, 1, negative 5 plus 4i, negative 20i, and now I'm going to use negative 4i. Negative 4i, bring the 1 down. Negative 4i times 1 is negative 4i. Oops, let's put her here, negative 4i. So if I add straight down, these cancel, it gives me a negative 5. And I multiply, I get a positive 20i and 0 again. My depressed polynomial here is x minus 5, and x minus 5 is equal to 0 when x is equal to 5. So in this case it says, find the remaining zeros. Those would be the remaining zeros. I was already given 4i, so negative 4i and positive 5. Alright, now, this one's a little kinder looking, at least, because they give you an integer here as the 1 0 that's given. So let's go ahead, do a little synthetic division here. Negative 1, so that's 1, that's negative 1. That's negative 4, that's positive 4, that's 5, that's negative 5, that's 0. Alright, now what I have left is my depressed polynomial is a quadratic. This is x squared minus 4x plus 5. So if I want to know when it equals 0, I would solve this, and you would hope maybe it factors, but it does not. So you're going to have to use the quadratic formula here to find the other two zeros. They're going to be irrational numbers, most likely. They might be imaginary, we'll find out. X is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, I think they're going to be imaginary, all over 2 times a. So that's going to be 4 plus or minus the square root of, this is 16 minus 20, negative 4, all over 2. So this is 4 plus or minus, this is 2i divided by 2, and 2 goes in the both, that would give me 2 plus or minus I. So it says find the remaining zeros. Well, the remaining zeros (2 plus or minus I), and that would answer that problem. So again, these are problems. I know it's not quite using Descartes' rule of signs, but it is in this section, and these are on your review for your final.